We don't know the direction of the velocity. That's right. We always know the magnitude.
Okay.
Because the 1/2 mv squared is this number.
Yeah.
And so but all that means is I don't know whether v is plus or minus, because I know what v squared is, but that leaves a sign ambiguity in v.
Okay. Yeah,
In 3 dimensions, though, it would be an even bigger ambiguity, because then I would know the magnitude of v, but it could point in any direction at all, in any one of an infinite number of directions. In 1 dimension, it can only point 2 ways, it's either left or right.
okay.
So it's worse in higher dimensions. Okay, is that clear?
Yeah.
All right. So force fields lead to work and potential energy. This is just a 3-dimensional view of what we've been doing in 1 dimension. So there's absolutely nothing new here at all, except maybe a vector dot product. So for reference, this is my coordinate system. dr is some infinitesimal displacement in 3-dimensional space in some arbitrary direction. Here I've got in 3 dimensions now. So now this is 2-dimensional motion here. Like these are 2 axes of motion. Unlike the previous graph that was 1-dimensional motion. The question is, how does UAB, the difference in potential energy between A and B, compare to UAC? What do you think? Given that force field that I've drawn, that's uniform in that region. It's the same. Why?
Forces or energies consumed?
Because what?
Well, I imagine they would use the same. I think it's because it's relevant to the path.
It's independent of path, but I'm talking about 2 different points. I'm talking about potential energy from A to B versus potential energy from A to C.
The field is uniform, that's right.
Yeah, the field is uniform to the right.
Because the length in the direction parallel to the force is the same, or the magnitude of the displacement parallel to the direction of the force is the same.
Because the magnitude of the displacement parallel to the force is the same for A to C and A to B. And what is the significance of the magnitude of the displacement being parallel to the force?
Because there's no if the force is parallel, then the acceleration perpendicular to the force is 0. There's no.
Right, the work done perpendicular to the force going from A to B is 0. In other words, the parallel components, that's the dot product. The work done is the product of the parallel components of the force and the displacement. And so the parallel components from A to C and A to B are the same. Right? The parallel component of the displacement parallel to the force from A to B and A to C are the same. Another way to look at that is I can get to C. The work done is independent of path. I can get to C by going through B first and then coming straight down. But when I come straight down, my displacement is perpendicular to the force. So what's the work done?
0.
0. Right? How much work does it take to roll a ball across this table with the force of gravity being straight down? 0. Gravity doesn't affect it moving sideways. It only affects it moving up and down. It only affects it moving parallel to the force of gravity. So if I can get to C by going from A to B first and then doing 0 work from B to C, then the total work from A to C is the same as the total work from A to B. Is that clear? So in 3 dimensions, we have to use a line integral in order to evaluate the work, because our path can be any weird, crazy path through 3-dimensional space. And so we break up our path into a bunch of little tiny displacements. And every displacement might point in a different direction. Like earlier, we had one where the path was curved. And so every little tiny displacement on that curve points in a different direction. And so every little dot product has a different cosine factor in it, because the theta might be different at every single infinitesimal increment. And so there are times when that integral is hard to evaluate, because you have to know a lot of stuff. But in principle, it is possible to evaluate it. And so that kind of an integral is called a line integral. It's a 1-dimensional integral, but it's weaving its way along a path through 3-dimensional space. And so dr is a vector, and f is a vector, but it's still a 1-dimensional integral. Is that clear? It's 1 dimension because we're going along a path, a 1-dimensional path. So in order to evaluate that, you usually have to have some kind of symmetry or some kind of information that you can use to get rid of that cosine factor and turn this into an ordinary integral. Because those are the only integrals we really know how to evaluate. Right, so that's the trick to doing line integral problems. I don't know how deep you're going to get into line integrals in this course. But,
We hasn't done it
yeah, okay. So just keep that in mind for when you get to your future classes, because you will see this again, believe me. So just like in one dimension, the work done is independent of the time, it's independent of the speed, it's independent of the path, same reason. So we can also do the reverse. We can go from the potential energy back to the force field, and that's the gradient operator. If we move some displacement ds, which probably should be called dr. Yeah, that should be dr. So here's some dr in space, and if we blow it up, because it's infinitesimal, so it's small, but if we blow it up here so we can see it bigger, that should be dr on that arrow. We find that the x component of the displacement will do some amount of work that's related to the x component of the force. The y component will do some amount of work that's related to the y component of the force. The z component of displacement does some work related to the z component of the force. The total work done is just the sum of those three pieces of work. They're not components because work is not a vector. And so that leads to the gradient again. That's where the gradient derivation comes from. There, I fixed it. No time for the cover. Again, the gradient produces a vector field from a scalar field. So we have some equivalent statements about conservative fields. A force field is conservative if the potential is a function of position only. If I can write it as the potential energy U of r, it's a conservative field. I can also say it's a conservative field if the work done on a particle between 2 points is independent of the path. The work done by the field is independent of the path. It also has to be independent of the time. That is the time of day. Like if I'm turning up the strength of my electric field, then it's a time-varying field, and that means it wouldn't be conservative. We expect conservative fields to have these properties by conservation of energy. If they didn't, we could get an infinite amount of energy for nothing, and that would be great, but the universe is not that happy about it. So, as a bonus, which you don't need to know for this fact, but we can actually prove this explicitly from the force field itself using vector calculus and the scroll operator. I won't go into any details, but again, you guys, any electrical engineers here? Okay, well, this is going to be your best buddy. And for example, magnetic fields do have a curl, whereas electric fields, static fields don't have a curl. But that means the electrostatic field is conservative and the magnetic field is not. Right? So there are non-conservative forces that you will have to deal with. You'll get some of this in 2D as well. Okay, center of mass. Dr. Carr did center of mass. I'm just reviewing this quickly. For many purposes, not all, but for many purposes, a system of many masses, or a distributed mass, like a baseball bat, where the mass is distributed continuously throughout the space of the bat. But for many purposes, the system behaves as if all its mass were concentrated at a single point, and that point is called the center of mass. It's often abbreviated COM, and a way to think of it is the mass-weighted average position, where position is a vector in general. So in one dimension, the center of mass is just the sum of, is the weighted average of the x positions of the particle, and the weights are the masses. So heavy masses count more in determining where the center of mass goes than light masses do. But since it's an average, in the end, you have to take this sum and divide it by the total mass. And that gives me a position, right? Check out the unit. X is position, m is mass. Position times mass divided by mass is a position. So the center of mass is a position in space. And for 3D, it's similar. For y, and z, it means we can write this as a vector equation. And the left-hand side is a vector. The r center of mass is a position vector. It's got 3 components, x, y, and z. Every position of every particle is also a vector. So this is a vector equation, which is different than a number equation. A number equation has a number on both sides. A vector equation has a vector on both sides. Could I ever have an equation with a vector on one side and a number on the other? So dot product, but when I evaluate that dot product, it turns into a scalar, a number. So in the end, the quantity on the left, could the resulting quantity on the left ever be a vector, and the resulting quantity on the right ever be a number? Yes? What's an example of that?
The quantity on the left is R dot R, which is two vectors, so the quantity on the right is R.
Right, so R dot R on the left though is a number, so the net quantity on the left would still be a number, even with a dot product.
Okay, no, but you're jumping to vectors, right?
Right, the dot product of two vectors is a number. Okay, so if I say R dot R equals 3, this is a number, and that's a number. Right, the dot product of two vectors is a number.
Okay,
Could I ever have something like R vector equals 3? No, that's totally meaningless. Right? So I either have a vector equation where both sides are vectors, or I have a number equation where both sides are numbers. Later on, you'll have matrix equations where both sides are matrices. Okay? So in this example for center of mass, it's a one-dimensional system. I have a big mass on the left, I have a little mass on the right. The big mass counts more, the little mass counts less, but it still counts for something. The center of mass is somewhere between them, but it's closer to the big mass than it is to the little mass. And if I balance this system at its center of mass, one of the properties is that it balances perfectly. It won't tip one way or the other. If I try to balance it over here toward the big mass, it'll fall over to the right. If I try to balance it over here, it'll fall over to the left. Okay, thank you.